Hey everyone, welcome to today's Explainer, where we're going to break down the foundational objects and mathematical actions that make up circles. If you've ever thought about how we mathematically define the parts of a circle, and honestly, how we measure them without getting completely tripped up, well, you're in the exact right place.
Okay, here's our roadmap for today. We'll cover 1. Lesson objective, 2. Essential circle vocabulary, 3. Central angles and arcs, 4. Analysis of measuring arcs, 5. A quick misconception check on arc measures, and finally 6. A formative check and recap.
Section 1, Lesson Objective. Let's establish exactly what we're going to master in this session. By the end of this explainer, you'll be able to speak the geometric language of circles fluently. Plus, you'll understand the absolutely crucial difference between an arc's measure and its physical length. That last point, that's a spot where a lot of students stumble. But don't worry, we're going to give you a bulletproof framework to ensure you get it right every single time.
Moving on to Section 2, Essential Circle Vocabulary. Let's get our fundamental definitions locked in.
You really can't build a house without knowing what a hammer and a nail are, right? In the same way, you can't analyze a circle without knowing its structural components. We start with the circle itself and the radius, which establishes that exact given distance from the center point to the outer edge. Just imagine a single point on a flat plane. Now imagine every single point that is exactly 2 inches away from that center point. If you connect all those outer points, boom, you've drawn a circle. The radius is literally just that straight line representing that exact 2-inch distance.
Now, if you were to walk all the way around that outer edge, that total linear distance is your circumference. Think of it as the perimeter of the circle. If you took a pair of scissors, snipped the circle, and laid the boundary out flat into a straight line, the length of that line is the whole circumference.
But what if you don't go all the way around? If you only consider a fractional portion of that circumference between two specific points, that unbroken part is called an arc. It's essentially just a continuous curve along the circle's outer edge. If your arc perfectly divides the circle exactly in half, aligned right with a straight diameter line passing through the center, you've got a semicircle. This represents exactly half of the total circumference.
So, following that logic, any smaller, shorter portion is appropriately named a minor arc, while the remaining larger portion is the major arc. It's a super simple way to categorize arcs by size: minor for the short path between 2 points, and major for taking the long way around. All right, Section 3, Central Angles and Arcs. Let's see how we go about connecting these objects.
Notice how the angle at the center point P opens outward, establishing the strict boundaries for the minor arc from point A to point B. The angle literally sweeps across the interior of the circle, and right where its sides hit the edge, it creates that specific arc. In geometry, we say the angle intercepts the arc. This is officially defined as a central angle because its vertex is locked right at the center, and its two sides are straight radii extending to the edge. It's called a central angle simply because its vertex is sitting at the dead center of the circle. Makes sense, right?
Section 4, Analysis, Measuring Arcs. Let's apply some quantitative reasoning here. To avoid any confusion, we're going to use a quantitative reasoning framework to break down the exact attributes of what we're measuring. By just slowing down for a second and defining the object, its measurable attribute, and the units we use, we can completely avoid the most common traps in geometry.
See how clearly this separates the two quantities? Arc length measures physical distance in linear units, like inches or centimeters. On the flip side, the central angle measures geometric openness in degrees. If you take away just one single thing from this explainer today, let it be this framework. The attribute of the arc length is actual physical distance. You measure it with a flexible ruler. The attribute of the central angle is openness. You measure that with a protractor.
Section 5, Misconception Check, Arc Measures. Let's clarify these measurements.
It is incredibly easy to mix these up, so I want you to really ask yourself, does finding the arc length mean you are finding the arc measure? If a problem asks you for the measure of an arc, can you just give them the answer in centimeters?
The strict answer is no. Length is measured in linear units like centimeters with a measuring tape, while arc measure is always in degrees, defined entirely by the central angle that intercepts it. By definition, the degree measure of a minor arc is exactly equal to the degree measure of its corresponding central angle. But the physical length of that same arc, that's just a fraction of the total circumference. They are two entirely different ways of describing the same geometric object.
Section 6, Formative Check and Recap. Let's review the concepts. Take a look here. Can you mentally identify both the central angle and the specific minor arc it creates? Notice how the vertex sits right in the middle, and the highlighted region flares outward toward the edge.
If you pinpointed angle AOB as the central angle and that outer edge AB as the minor arc, your geometric reasoning is spot on. The central angle AOB effectively projects out to the circumference, carving out minor arc AB. To recap our explainer today, circles rely on radii and central angles to define their boundaries, and you must absolutely always separate the linear length of an arc from its degree measure. Always remember our quantitative framework. Ask yourself what object you're looking at, what attribute you're measuring, and what units are actually appropriate.
I'll leave you with this final thought to ponder. If a circle expands massively in size, its central angles won't change their degrees at all. But what does that mathematical truth mean for the linear distance you'd actually have to walk along its arcs? Think about two circles, one the size of a coin, one the size of a football stadium. The 90-degree central angle remains a 90-degree opening for both of them, but the physical distance you walk on that arc, that changes dramatically. Keep that framework in mind and you'll never confuse the two again. Thanks so much for learning with us today.